Well, this is going to be an introduction to capacitors. What are capacitors? Well, capacitors are whenever you have, um, when you have two conducting materials that are distance apart, and so you can have a charge or a difference in charge accumulate on them, and they can store energy. So, um, the capacitors we are going to be dealing with right now are called parallel plate capacitors. So parallel plate capacitors look like this. They are going to have um, some material here. These are going to be really in two dimensions. So it'll look, we'll call it, it doesn't have to be a square shape, but I'll just draw it as one for make it easier to see. You have, these are two um, conducting surfaces or materials. So conducting materials here. And they are going to be separated, or first you see that they are going to have a surface area, and we'll call that equal to A. So this is the surface area. And then this is the surface area of overlap. So this is only the surface area that they have in common. And then they are going to be separated by a distance d here. And we'll use these variables later for to calculate the capacitance given a set of like a certain situation where you have some materials. And then in between these conducting surfaces, you're going to have something called a dielectric. So this is going to be in the gap or in this space in between these two conducting surfaces here. So if we look at it from a side view, like a straight on side view, it'll look like you have this conducting surface. Sorry, these should be parallel because it's a parallel plate capacitor. And then you have the dielectric in here. So this dielectric, it doesn't have to be like a physical material. Like this could be like a vacuum, or it could be like um, air, or it could be some like other material here. So it could be a solid, like, but it doesn't have to be like a physical material. It could even be a vacuum. And now this dielectric will have a property. Dielectric will have a property K, or it'll have so dielectric constant, and then for this will come in handy when we're calculating capacitance. But you know that for a vacuum, we have K is equal to 1. And then for air, we have K is going to be a little bit greater than 1, but it's roughly equal to 1. And then for other materials, we have K is going to be greater. So K is going to be greater than 1 um, when it's, or K should be greater than 1 when it's an insulating material that's not a vacuum. And the role of this dielectric, what it does is that it prevents electrons from jumping this gap. So if you have a charge difference, it helps maintain that charge difference before charges can start going from one to the other. Um, so the dielectric is there to prevent electrons from jumping the gap between the capacitor. Now, given these variables, we can calculate the capacitance for a capacitor. But first, let's get into what is capacitance. So a capacitor will have a capacitance, and that means that. So when you have this parallel plate capacitor, and if you draw a graph of the voltage difference here, so this is going to be the voltage difference, or like this is going to be the voltage between the plates. So the potential difference between plates. And then you have Q here. and then this is going to be the net charge um, on each plate. So this is on each plate, not the total charge difference, but this is the net charge on each plate. And you graph the line between these. So if you have a charge accumulated on one plate, there will also be a charge on the other plate for this capacitor. It will form a straight line. So this will be a direct relationship, and the slope of this will be capacitance. So this is the definition of capacitance, or capacitance C. So it's the variable is C, capital C. So C is going to be equal to voltage over charge, and is going to be the slope of this. And then this is a property of capacitors. So a given capacitor will have a given capacitance. Like if you have an object, it has a certain mass. Or if you have like something that's at a certain temperature, a capacitance depends on the conditions of the object. It is not constant. How do you calculate capacitance? Well, we have, based on these variables we're given, capacitance is equal to K, this dielectric constant, times E0, which is permittivity, times the surface area in common, divided by the distance between the plates. So from this, you can see that capacitance is proportional to surface area. Capacitance is proportional to the dielectric constant. Capacitance is inversely proportional to distance. So as we increase the size of the plates, capacitance is going to increase. Or if we increase the dielectric constant in between these, so as to stop the electrons from jumping across and to allow a greater charge difference to build up, we also increase the capacitance. But if we increase the distance, that brings them further apart, and so they'll have like weaker interactions between the plates. So that decreases capacitance. Okay, and then now capacitors can store energy, and we know that by the definition of voltage, we know that voltage is going to be equal to change in energy over charge. So now we know that, or change in voltage is equal to change in energy over charge, but then we know energy is equal to change in energy is equal to change in voltage times charge. So capacitors, instead of UE, it will denote it as UC. And if you look at this graph, you see that the area of this graph is just the charge times the change in voltage. So area here is going to be equal to UC. And so from this, we get that the area is going to be 1/2 Q change in V. And so this is the amount of energy the capacitor stores for given charge and voltage. But from this this equation here, we can substitute in charge here, and we get that UC is also equal to, so we have Q is equal to CV, or change in voltage here. So we can use change in voltage. So Q is equal to CV, which means that the energy stored in a capacitor is also equal to 1/2 C change in V squared. So this is also how you can find energy of a capacitor. Or you can even substitute for voltage. So voltage is, sorry, as in Q. So capacitance should be, it shouldn't be Q over, so capacitance, since it's the slope here, it should be charge over voltage, not the other way around. That was a mistake earlier on. Capacitance is the slope of this, so again, it's charge over change in voltage. And then Q here is going to be equal to capacitance times change in voltage, so we can substitute this in. But we can also substitute for voltage in here, so we have voltage is going to be equal to Q over C. So charge over capacitance. And then we get that the energy a capacitor stores is also equal to 1/2 Q squared over C. So these all are equivalent ways of finding the energy stored in a capacitor. So one thing about these capacitors, parallel plate capacitors, that's really important is that we are assuming that for parallel plate capacitors, that D here, so the separation of the plates is small. So this is separation of plates is small compared to the surface area of the plates. So surface area in common is large. So both of these conditions have to be true. So the separation of the plates has to be small relative to the surface area. And why this has to be true is if you look at an electric field diagram here, for two capacitors, the electric field is going to be, these equations assume a uniform electric field in between the capacitors, which means that the electric field will be like straight lines like this. These connect to the end, but they're going to be evenly spaced apart. So these are the conditions necessary to use the equations for capacitance, to calculate capacitance. And so this capacitance relation doesn't depend on this geometry of capacitor. This holds for all geometries of capacitors, but specifically for parallel plate capacitors, in order for this equation to be true, we need it to have a uniform field. So a uniform electric field. Now the reason that this area has to be large and that the separation has to be small is because as area becomes smaller and separation increases, you get that in the center this field is still uniform. But then over here there's going to be a net, the field is going to start curving because like at this point here, there's going to be more, if we're assuming this is the positive side. So let's just assume that this is the positive side and then the other side is the negative side. So this is the negative side here. If we're not centered on it, then there is going to be greater force upwards from these this charge than downwards. So this net force is going to be upwards. And so as but if we have like a really large plate, then this force here, like the upwards force and downwards here force, are going to be pretty much equivalent because there's so much charge on either side that it basically cancels out, and so it goes straight. But as this becomes smaller and the distance increases, the asymmetric geometry of this, when it's not centered, is more apparent. So the capacitor, if this area is small and the distance between like these plates is big, then these field lines are not going to be uniform. They're going to start curving out. And then this makes sense because the area in the middle is going to have less net force than the areas on the edges of this because it's going to be closer to the charge. Whereas these are so close that the distance to this surface doesn't really affect the field strength that much. So especially at the edges of these, the field is going to be like, it's going not to be uniform. Even in this, the edge of this is not going to have a uniform field. So when we're dealing with capacitors, we are assuming that the distance is small compared to the area, and then we are going to ignore edge effects. So we're ignoring these curved parts of the electric field because that's going to go against our assumptions of what a capacitor is, and they're small enough usually when these conditions are met that they're negligible. But it has to be that the surface area is large and the distance between these is small. Okay. And then finally, since this is a uniform field, um, we can also derive an expression for the strength of this field given these um, assumptions. And one more assumption we can make. So this is the strength. So field strength. And then another assumption in addition to those previous assumptions is going to be that K is going to be equal to 1. Now remember, for K is equal to 1 when it's in a vacuum, and when it's in air, K is roughly equal to 1. Like, it's really close to 1. But so when K is equal to 1, we know that electric field strength is equal to change in voltage times, so this is magnitudes, times change in position. Or change in voltage, sorry, not times, change in voltage divided by a change in position. Now we have that the voltage here is going to be equal to a charge over capacitance. So we have this is going to be equal to charge over capacitance times change in R. And now we find that capacitance is going to be equal to, remember, capacitance is equal to K epsilon naught A over D. So this D here is going to be the same as this difference in R, because we have the voltage is going to be the voltage across both plates. So this radius, or this change in position here, is going to be the separation of the plates. So that means that this is going to be equal to Q over this, these cancel out here. Q over K epsilon naught and A. And since we know that K is going to be equal to 1, we have electric field strength. Electric field strength here is going to be equal to the charge over epsilon naught in area. So that is the magnitude of electric field strength. So magnitude of electric field strength here, given that K is equal to 1 and you have parallel plate capacitors. So we have these equations that are very essential to remember for capacitors. Now let's examine a situation, some situations with capacitors. So we can connect the ends of a capacitor to a battery. And so a capacitor, the schematic symbol for a capacitor is this. So and then the schematic symbol for a battery is going to be equal to this. So it's going to be a longer and a shorter side. And this is going to be positive. The longer side is going to be a positive side. Sometimes you can also see a battery, especially when it's multiple cells, look like this. So it'll be like multiple of these stacked together. And again, the positive side is going to be the longer side. Capacitor symbols also could look like it could be curved. And then sometimes when you have electrolytic capacitors, which have polarity, you'll see that like the positive side will be straight while the other side will be curved. Anyways, so if we draw like a capacitor, if we connect a capacitor to a battery here, so it'll just look like this circuit. The battery here is a constant voltage source. Which means that the voltage across these capacitor plates is going to remain constant. So what happens when we bring the plates further apart? Well, if the voltage is constant and we bring the plates further apart, then we know that since the change in, so this voltage is constant, but then this is going to be equal to electric field strength times this distance. And since the electric field strength is uniform and distance if this electric field strength is uniform and this distance increases, or so since voltage is constant and this distance increases, then the electric field strength must decrease. So since this is going to be constant and this increases, electric field strength must decrease in magnitude. So it's still going to be in a uniform field, but it decreases. And the reason it decreases is because charge also decreases on each of these, because you know that capacitance here is going to be inversely proportional to distance. So this is a D. And so if distance increases, so if this R increases here, then the capacitance is going to decrease. And if capacitance decreases, then we know that voltage is equal to, or capacitance times voltage is going to be equal to charge. So if this is equal and this decreases, then charge decreases. And if charge decreases, it makes sense that this field strength also decreases. So this is when it's connected to a battery. And if it's going the opposite way, then everything here is flipped. So if you get closer together, voltage is the same, but then field strength increases because charge increases and capacitance increases. Now, what happens if you just have two plates here that are not connected to the battery? So this is unconnected. So unconnected charged plates. What happens when you move them further apart? Again, this is assuming uniform field. So let's assume that these are really big and you're just moving them further apart by a little bit. Well, now we have charge is constant. So Q is constant. And then so now we know again that capacitance is going to be inversely proportional to distance. And so we have that Q is equal to capacitance times change voltage. So if this is constant and this decreases, then voltage has to increase. And this makes sense because voltage is related to is change in electric potential energy per charge. And if the charge is the same and you're bringing them further apart, then these are opposite charges, so their potential energy is going to increase. And what this also assumes is that this field is uniform, and since the charge doesn't change, the net charge doesn't change, the electric field strength also doesn't change. So this, in this case, the electric field strength is also constant. So if you have it connected to a battery, this field strength can decrease. But if you're not connected to a battery, charge remains the same and the field strength also remains the same. And so here, this voltage, the voltage between the plates is going to be then directly proportional to the distance between them here. Whereas here, the voltage stays constant, and then we have capacitance changing and field strength changing. All right, thank you for watching.